Yeah, so we were looking at quantum computing and basically trying to explore what kind of parts are classically easy, what is really quantum hard. We ended up employing a lot of existing automated reasoning methods to quantum circuit compilation problems. And that's why this talk is called the unreasonable effectiveness of these methods, because I will want to show you that out of the box, many of these classical satisfiability, decision diagram, these classical reasoning methods work really well in quantum circuit problems that we have. Yes. So I want to start with satisfiability, and in particular sharp sets, so model counting. And we have a reduction from simulation, exact simulation of quantum circuits and equivalent checking of quantum circuits to sharp sets. And the second thing I want to talk about are data structures for representing quantum information and manipulating quantum information. We studied several of them, starting from the stabilizer formalism and the generalized versions of that, supporting universal quantum computing, but also decision diagrams and tensor networks, and in particular the matrix product state, which is like a linear tensor network. And we were interested from a computer science perspective, what are the trade-offs between succinctness of these structures and tractability of operations. This is like the usual trade-off. If you make things more succinct, it becomes harder to apply operations to them. And yeah, this is more or less a summary of the results. What you see here is a state space of all quantum states and or families of quantum states. And we reason asymptotically, and we try to find families of quantum states that are small in one representation, but large in the other. And yeah, these ovals basically represent what we can efficiently represent in an MPS data structure, for instance. And this is what we can efficiently represent in an RBM, in a restricted Boltzmann machine. And these are decision diagrams, particular type. And we see that they are all incomparable in terms of succinctness, meaning that there are exponential separations in both directions. So there are states that are like polynomially sized for LIMDD, but exponentially sized for MPS and vice versa.
So just to clarify, so you want to store a quantum state classically. That's the
exactly, yeah, classical representation. And then the trade-off is, of course, if you become more succinct, you go maybe from a QMDD to a LIMDD, you have to do more work to implement operations on quantum states. So we study all these important operations, the gates, but also measurement, of course, equality, inner product, and computing fidelity in quantum states. And we end up with this diagram, which I will explain in detail, or this table, which I will explain in detail, showing that many of the operations are still tractable, but some of them become intractable once the data structure is more succinct. Okay, but let's get started with the sharp set methods. So we have a reduction from quantum circuits to sharp set. What is sharp set? It is also called model counting. So it's like the counting version of satisfiability. Instead of finding a satisfying assignment, we are asked to count satisfying assignments for that. And then there is a weighted version of it, and then we are given a formula in conjunctive normal form, and we are given some weight function, and the weight function basically assigns weights to variables, actually to literals. When the variable is set to true, it gets a certain weight, and when it's set to false, it gets another weight. And then the model count, the weighted model count of a function f is basically this summation here, where for each satisfying, or for each assignment, if it's satisfying, this will be 1, and this will be the weight of the assignment, alpha, where the weight is basically a product of the weights of the individual literals in that assignment. So when a variable is set to true in the assignment, it will get a certain weight, and it's set to false, it will get the other weight.
You said something about the relationship between quantum circuits and sharp set, but I didn't catch it, or maybe you're gonna say more.
We're going to basically reduce simulation of quantum circuits to this method.
So, sorry, what is this capital V?
This is the weight function.
No, not
Is that a variables, I think?
Which one? Capital V.
V.
Yeah, these are the variables of the.
So there's like n variables. Is that
Yeah, there are n variables. And basically for each variable, we check whether it's set to true or false in this current assignment alpha. And that gives us a certain weight. According to this weight function. Yeah, okay, I should say that indeed this bar V means that the variable is set to false. And V means it's set to true in the assignment. Okay, small example. So we have the formula A or B and C. There are these three satisfying assignments, and according to this weight function, they will get this weight because we only give a weight to the variable A. If the variable A is set to true, we get this weight, and if it's false, we get this weight. So in the end, it's just a sum of the weights of all these assignments. This is the model count, the weighted model count of this formula. Okay, there are no questions, then let's go to the reduction. We start with a circuit like this one, and basically we assign certain Boolean variables to the qubits. We will call them X and Y, and to the gates H and T. What we will be doing is we will do an encoding of the computational basis. So we need a different variable for each, let's say, amplitude that changes. Yes.
Yeah, sorry, I'm still confused about the weights on the previous slide. Are the weights for variables or for actual assignments?
I think the literal is like every variable has a weight and every negative variable has possibly totally different weight. Right?
The variable in a certain assignment, the variable is set to true or false. Yes. And this gives the corresponding weight. So, and these weights we are going to use to basically implement the amplitudes, for example, in this matrix, right? 1 divided by square root 2. And in this T gate, we have the rotation, the omega rotation. What we do is we're going to copy the X and the Y variables for every time step in the circuit. So I will just illustrate it informally what we want to do in the encoding. So we start with the 0, 0 state, and we will just encode it by setting X and Y to false. And you should read this as not X and not Y. So there's an implicit conjunction here. And again, we copy the variables for every time step. That's why I put the subscript 0 there. Then in the next time step, we apply the Hadamard gate. So we get this superposition with these weights. So what we want is basically use these next time step variables, X1 and Y1. And we only set X1 to false, and we leave, or sorry, we only set Y1 to false, and we leave X1 unassigned. Meaning that we get 2 satisfying assignments for this formula.
So the variable H, should that represent like, you could either apply the Hadamard or not? Or
well, actually, the only thing that this H represents is that the Hadamard has been applied and that there should be this weight over both, for both the computational basis states. So it's just, we set it to true, it's always true in this formula. So we just only get this weight. Later I will handle the other cases. So if you check, you will see that this formula will have 2 satisfying assignments because X1 is not assigned, and these correspond exactly to these basis states that we try to represent. And then the H is used to represent this weight. Now, in the next step, you want to encode the C0 gate. So then we get the Bell state. And what do we want? We want to have a disjunction between these two. formulas, so that we again have two satisfying assignments. And somehow we want to keep this H around from the previous computation, right? There's still this.
Can we view this as like we're trying to come up with a formula that will, whether it's satisfied or not will have something to do with this circuit or?
I guess you're trying to build a set instance that has sort of as its satisfying assignments, the bit strings and the support of
Yes.
that state that you have.
Exactly. So the satisfying assignment.
It's model count or whatever, it's
Yeah.
weighted model count that will somehow encode.
Represent the state, yeah.
We will use the weighted model count to get the amplitude of a certain wave.
But this is for doing strong simulation.
Strong simulation. Yeah. And then in the next step, we want to keep something around from the previous steps. We will keep this H around because we still have this weight around here. And also we use the T variable to represent this rotation, but only for the 1,1 basis state. So we should have something like a disjunction where T is set to false and T is set to true in part.
Can I ask a motivational question?
Yeah.
Is this model counting, is this something that we're good at in practice?
Yeah, so
Yeah,
there-
okay.
There are very good, maybe I should mention indeed, there are even competitions to improve these model
Okay, yeah,
counts.
so the reason you're doing this is because you happen to be extremely good at model counting and this might be a good simulator in practice.
Yeah, not me,
Okay.
but other
Yeah, someone is, yeah, okay, very good. Yeah.
So we can just feed it to the model counter and they solve the population problems. So if we zoom out a little, we can do a gate encoding. So we can create a formula for the Hadamard gate, where we have some input variable x, and x prime is, you can view like the output qubit, the result of applying the Hadamard gate. And this h variable is again this. And what we do is we leave x prime unassigned. We only use x and x prime. If these both are set to true, we make sure that the h variable is set to false. Well, why do we do this? Because we then want to have the weight minus 1 divided by square root 2. Because if we apply the Hadamard to the one state, we get a 0 plus a 1 state, where the new 1 state has a negative amount, right? Okay, and the encoding for C0 will be similar. You can think it out, but basically you can read this as the first qubit, nothing happens to it. And the second qubit, we only flip if the first qubit is set to true. And then the T gate, the X or the first qubit, nothing happens to, but then it gets the rotation whenever we apply it to the 1.
Also, the weights can be complex. Okay.
That's something I will get to actually. So how do we encode this circuit? We basically encode the initial state, which is 0, not y0. And then we conjugate all the formulas for the gates, where sometimes we also have to add the identity, right? So we apply the Hadamard to qubit X, and then we have to say that nothing happens to qubit Y. Just to, okay, we can do something smarter, but just not using these variables, but that's just implementation detail. And then finally, if we want to know what is the probability of measuring 0 on the second qubit, we just conjoin with negative y3, yn times the 3. Now, our claim is that if you take the weighted model count of this formula, then you get exactly the probability or the amplitude circuit. And there's one thing to mention in particular, namely if we look at constructive and destructive interference. So if we apply 2 Hadamard gates, after the first Hadamard gate, you get this the plus state. And then if you apply it again, you actually get this state where normally you see that there's this destructive interference, this cancels out, right? Because we have +1 and -1 here. But actually what happens in our encoding is that they don't cancel out. We just get 4 satisfying assignments. So we will create the following formula for this circuit. And the satisfying assignments are as follows. In the first time step, we only have one satisfying assignment. In the second time step, we will have two. And in the third time step, we will have four, representing all these things. So there's some kind of redundancy in there that we kind of leave to the weighted model counter to solve for us.
Sorry, where does the absolute value square happen? Like, are you trying to get the amplitude or the stability?
Only the amplitude.
Huh?
The amplitude.
But like in the previous example, aren't you gonna be adding an amplitude? Because like you're saying, you want to have the y equals to
Yes.
0, and then the first cubic is either 0 or 1.
Yes, I think you're right. Yes. I should have I should have done the measurement over all qubits, then it would be correct. Yes. So let's say, okay, sorry.
You really want a single amplitude.
Like a whole bit
because it
string,
would be like
yeah.
a sum of amplitudes.
Yes.
Which is a bit weird.
We can solve both problems, but okay, I made a mistake on this slide.
It should be 0, 0.
If we measure both zero, if we want to know the probability of measuring 0, 0. Then we get exactly that amplitudes. So then we should also add not x3.
Yeah.
Thanks for pointing out. There are a bunch of problems with this. First of all, if we want to check equivalence of circuits in the computational basis, we will have to check all these input states. So we want to avoid that. And we have the complex weights in there. And actually the modern model counters do not support complex numbers. So what we do is we actually move from the computational basis to the Pauli basis. And how does this work? Well, we have a quantum state. We instead represent it as a density matrix. Anybody not familiar with density matrices here?
I have a question about a different way to get rid of the complex amplitude is to use a different universal gate set, namely Hadamard and CC naught.
Yeah.
Which is also what is typically used when you show that BQP lies in PP.
Right.
And that proof has a very similar sort of counting complexity result in the sense that you write the amplitude as an exponential sum over many terms. It should be like a Sharpie computable function then.
Yeah, we indeed, but then it would not be easy to, we would take a practical approach. So we also benchmark this in circuits. Then we would have to translate all the circuit to approximations in this case. So
You really want the language of logic here because you have like solvers for that. That's what you're saying.
yeah, and we want to support every gate set. We can actually support also arbitrary rotations, so that we can, we can deal with any existing.
And I guess again, just sort of the main motivation here isn't to sort of state some complexity theoretic result, it's to actually, put this in a machine that spits out equivalences.
That's empirical.
Yeah.
Yeah, that's a good point. But we focus on supporting large gate sets. So how does this work? We represent the state as a density matrix, and then we can decompose this density matrix in the Pauli basis. So what we see is that this I state, if we take the density matrix, it decomposes like a y plus an I Pauli. In general, this holds for n qubits. So we can take the n qubit density matrix, and then the Pauli decomposition is basically a weighted sum over Pauli strings, where a Pauli string is some Pauli's in parallel, right? So we go to this Pauli basis, and we can do the same thing, where I should note that now if we apply a gate to a Pauli string, we have to conjugate the gate on the Pauli string. So if we apply a Hadamard to a Z Pauli, we get an X and vice versa. And in general, you can work this out for all the Pauli strings, for all the Pauli strings and for all the gates. And this part is for the Clifford gates. And this is well known, of course. If you put a Pauli string in, you get a Pauli string out. If you go to the non-Clifford states, you put a Pauli string in and you get a linear combination of Pauli strings out. So in particular, if we do a T-gate, if we have a T-gate in the Z Pauli, we get Z again. But if we apply it to the X Pauli, we get X plus Y. So now we are going to represent this in our encoding, and we will use the following variables. So we will use now for 1 qubit an X and a Z variable. And if we set them both to false, then this represents the I Pauli. If we set X to true only, then it represents X. If we set Z to true, then it represents Z. This is basically the encoding that also Gottesman and Arends use in the paper. And then we can do the same thing. We can just do the gate encoding as before. And now for the Hadamard gate, we have two input Boolean variables X and Z, two outputs X and Z, and a sign, whether it's positive or negative. What should happen? Well, we swap the X and the Z. So the new X becomes Z, and the new Z becomes X. And that's basically what should happen, right? If there's a Z coming in, an X goes out. And if there's a Y coming in, then both X and Y are true. Or sorry, if there's Y coming in, both X and Z are true. So we have to set X and Z true again. And we have to flip the sign. So we get minus Y. And that's basically what happens in this conjunct. Sign is only set to true if both X and Z are true. Now we can do the same thing for the T gate. Okay, you can figure this out what really happens here. But again, we have this additional T variable which will represent this weight, 1 over square root 2. And we leave the X variable unchanged afterwards, because if X is set to true, then it will remain true in both the summation parts, right? And if X is set to false, then we have a Z or an I, and we get again a Z or an I. So we do nothing with X basically. This is the interesting part. This basically says that we make sure that Z is assigned only when X is set to false. What does this mean? Basically, it means that if we put a Z or an I in, so X is set to false, then we get again an X or an I out. That's why we have this part, leaving Z unchanged. But if we put an X or a Y if we apply a T to an X or a Y, we get again X and Y combination of. Therefore, if X is true, then Z should not be constrained, let's say. And by leaving Z unconstrained, we get this summation. We get two satisfying assignments representing this sum of values. Okay, so this solves our problem. We can now do encoding of circuits, and we get, actually now we don't get amplitudes out here, but we immediately get the probability out. And we can do it for any gate sets, also for these arbitrary rotations. And the encoding is actually linear length, because all these formulas are constant for every gate, constant size. So we implemented this, and we compare the weighted model counting approach against ZX calculus and decision diagrams. And we use some random circuits mimicking, for example, quantum chemistry applications. And what we see is that, okay, there's an exponential or log scale here. So there's an exponential trend, of course. But this is much less pronounced with the weighted model counters, which to us was kind of surprising, because we use an off-the-shelf weighted model counter. It's not tuned for quantum computing yet, and it already performs quite well.
Why do you think T counter is a good metric here?
Yeah, because it gives this is what you put in the satisfying assignment.
Oh, okay, yeah, yeah. So it's sort of a similar stabilizer states. Yeah. But it is true that things with more T gates tend to lead to more complicated formulas.
Not necessarily more complicated in the sense they have more satisfying.
Yeah. Okay.
So also for the generalized stabilizer formalism, this would be hard.
But by the way, like this formula, it comes out, it has this kind of like time structure that you keep adding more and more variables. So like, and the next variables are determined by the previous ones. like, is that something, because these model counters are probably, they are kind of more general. Like maybe it is something they can exploit in addition.
Yeah, I think they are already very much tuned for this kind of structure because they're applied to model checking.
So this kind of structure is common in other.
Yeah, there you also like in classical, they do verification, classical computations, and then you also have these timestamps, right? I think they do a lot of pre-processing too.
How much of this is just the model counting people being really good at writing C code? Because I can see like I like the thing you're comparing with is Alex and John. I'm not sure how good of a programmer you are. You know what it's like, it's not like this is their job, right? These are people that are extremely good at a particular thing and making it very fast. So how much of this exponential like will go back up later as you sort of run out of optimization in the model counting machinery?
Yeah, I think John's tool is also pretty well.
How fast is it?
It's a Rust, so it's.
Oh, okay, I retract what I say, it's pretty fast.
But I go to these conferences and there are some rigorous methods.
Yeah.
Some good smart heuristics in the model counters that really exploit, for example, the tree structure, the tree width of the
Yeah.
formula, and do all kinds of smart things.
Yeah, so I mean, these are professionals,
Yeah,
they know what they're doing.
I'm pretty sure they put more effort into.
This was sort of my point, like,
Yeah.
you also do other things, you're not like spending your entire day making your ZX calculus simulator slightly
I
faster.
should also say that very recently, someone else, like together with Alex, they made a new method based on physics. And like they claim it can be up to 1,000 times faster than what we're
Okay.
doing. So that might change.
Yeah,
the
I guess this
here.
is my broader point somehow,
Yeah.
like, how much of this figure is just 30 years of optimization in the model counting world?
Well, yeah, a lot, and they have very good implementations, but they have like one thing to mention that they have not tuned their tools for
Yeah.
this kind of problems.
That's
So
fair.
now it will be interesting to get both worlds to compete. Yes.
How did you measure the time on your process? Because it looked like there's this like baseline offset that looks like process starting up or something. And I would be interested in like, because like if you then subtract that, it looks very linear. I guess.
Well, it's
Like,
a-
have you tried it for longer? I guess is my question.
It's a log scale, right? So it's exponential.
Yeah, but if I could read it correctly from back here, like your red line is always under 10 seconds, right?
Yes.
Red line is like 20.
Okay, we should take it offline because my PhD
Yeah,
student,
yeah.
I don't know. Can figure it out.
I know that these are mostly think about maybe in this context, but has anyone thought about like quantum algorithms for model counting instead?
Quantum algorithms for model counting.
Yeah. I mean, I realize that would be not make any sense here because
I think what we have is the quadratic speedup, isn't it? Standards.
Yeah.
So,
I don't know.
but then I think the problem with these quantum algorithms is that there are no heuristics in there.
Yeah.
So I think in practice, you will never beat these kind of advanced approach that use the structure of the formula. You're basically, you would be comparing the heuristics versus brute force.
Because I mean, there are, like, there is, you know, at least some, like, there are, quantum algorithms for like SAT solving that I guess they use heuristics in the sense of like, they can speed up sort of they can get a quadratic speed up over the number of nodes you go to in the tree, so.
Yeah.
For example.
Quantum research.
There's no quantum speed up on, but like, yeah, I just wondered if people also had looked at the same sorts of things for model counting.
No, we have actually used quantum tree search to implement DPLL, or actually it was already done by others, right? But the real problem is like class learning. What makes these satisfiability tools so fast is that they actually learn information from your formula. They while they are exploring the formula, the structure, they add further constraints and then they constrain the search space. And this is, I think, this is interesting to look into. Can we also do this in the quantum tree search approach?
But that's just for SAT, I guess, already.
For
For
SAT.
the count, like for the counting.
For model counting, I think they have similar ideas. So I think you really need these heuristics to be competitive. But you're right, maybe we can use some of this tree wave also to get better quantum algorithms parameterized. It's a good point. Okay, let me continue. So we also do circuit equivalence with this, where the definition of circuit equivalence is basically you get two unitaries and you're asked to decide whether for every input state you get the same out up to global phase. So there's some global phase C. I need one definition. I will write for every single qubit gate P, Pj, meaning that I apply this gate on qubit J, where the rest is all identities. And then we have a textbook theorem, more or less, that states that to check whether U and V are equivalent, we only have to check whether conjugating the circuits on these Pauli strings, 2n Pauli strings, results in the same Pauli string. That basically checks it for the whole basis. So if we have this, we only have to do these 2n checks, and then we know that the circuits are equivalent. And we worked this out for Clifford circuits before, showing that this gives a very practical algorithm to Clifford circuit equivalence. And now we want to do it for universal circuits using our encoding from previous slides. And basically what we can do is we can use the encoding that I showed before and implement this. And if the model counter gives 1 back, then and only then we know that this holds for Pauli string. So again, we use the model counter, and again, we use the encoding that we saw on the previous slides with some small modifications. And if we implement that, we can also use model counters to check circuit equivalence. And for some quantum algorithms, for a set of circuits, we get these results, again, comparing against the decision diagram method. This is called Quasimodo and ZX. And we see that, okay, the model counter doesn't perform really well for most of them, but for VQE, for QFT, and for the W state, it beats the other methods. We implemented this in a tool called Quokka Sharp, where it's basically a Python library which does the encoding for you. It creates a linear length sharp set formula, and then it can do simulation or equivalence checking. So if you want to reuse this, then please check out the tool which is available on GitHub. Yeah, that was the part about sharp set. I would like to continue to decision diagrams, unless there are any questions about this part. Yeah.
How far can you push this simulation? So sort of your circuit was still pretty, like your curve was still pretty flat, right?
Yeah.
What's the largest circuit you've simulated?
Yeah, I think this is more or less it for the simulation. After this, it becomes interactive.
Oh, it just bumps up immediately, or
I'm sure on the next. Let's take this offline.
this is a very like it's sort of a very dramatic like up.
Or it just stops.
Oh, okay.
Like an.
There's existing good software for model counting. Does this do exact model counting or approximates?
Oh, that's a very interesting point. It's exact. And the next task will be, can we use the approximate counters? Because they use very nice theory indeed. They use this XOR constraints to split the search space, and then they only sample a subspace, and they extrapolate from that. I think.
So we also briefly looked at using approximate sharp set for like doing circuit simulation. But the problem there was that you get exponentially many amplitudes and they all interfere in like positive negative ways. So then the precision you need is also exponentially high. If you get like a random circuit, the amplitudes are exponentially small. Like, so then approximate doesn't really get you anything. You still need to have
Yeah,
exact.
so because of the negative weights, the cancellation, the constructive interference, and the destructive interference, these methods, the approximation methods, don't work. What we can do is we can create a formula for all the positive weights and the negative weights and do 2 calls, but then the approximation kind of gets too big.
Some of the positive can be huge, some of the negative.
Yeah. So, but I have some friends in this community and we're still looking into this. Maybe we can generalize these approximate methods because I think they're very nice, very exciting.
So the benchmark circuits, what kind of circuits were they?
Yeah, here I only show random circuits, but we also checked on all the existing benchmarks from this MQT benchmark set, and there's many more in the paper. I would have to take it offline because I.
Could you, like, if you have like, could you make a separate formula of say a Toffoli gate and then like help the model counter a bit by saying, oh, I know how Toffoli gate goes and it's classical, so it's probably like easier to do with a Toffoli than just like expanding it into T and like making a very big formula that will introduce lots of new variables.
I think in the computational basis, we do this. Also for decision diagrams, they do this. In the Pauli basis, it's a little harder. I tried to do it and
yeah.
it exploded a little bit.
Yeah.
Our goal is always to support as many gates directly as possible. Some we do via translation. Okay, so I want to move on. I have like, how much time do I have? Like
2 minutes or so.
Okay, so I have 20 minutes left to talk about the classical representation of quantum information. And I want to talk about the stabilizer formalism, decision diagrams, and our own LIMDD. What is the stabilizer formalism? Who is not familiar with the stabilizer formalism? Yeah, I will go over. Basically, it's a non-universal. The stabilizer states are a subset of all quantum states, and they are an important subset. So they represent kind of the entanglement structure of states, and they are used in quantum error correction, many other applications. So I would argue if you cannot support stabilizer states in your data structures for representing quantum information, it's not really a good data structure, right? Why are they so interesting? Well, there is a formalism for efficiently representing stabilizer states. And yeah, from an implementation perspective, let's say, basically we can take a stabilizer state phi, and we don't have to represent the entire exponentially sized amplitude vector, but we can represent it with a set of n of these Pauli strings, where the length of each Pauli string is also n. So we get a quadratic structure representing the same state. Well, there's some algebra behind it, but basically it turns out that these state or these Pauli strings, they stabilize the specific stabilizer state that they represent. So if you multiply the Pauli string with the state, you get again the same state. And these are basically the generators of some larger group that represents the stabilizer state. Okay, there's a very nice theory by Neil behind it. So basically, if you don't know the details, you can think of it like we don't have to represent the exponential amplitude vector. We just have to represent this quadratic structure, and we can compute on that. And indeed we can, because if we apply a Clifford gate on a stabilizer state, we again get a stabilizer state. And we can also implement that efficiently on this tableau structure. Basically, we update one column of the tableau to apply a Clifford gate, or 2 columns. So stabilizer states and Clifford circuits are efficiently simulatable using this formalism. Okay, some details. The 0 state is stabilized by the Z Pauli, the 1 state is stabilized by the minus Z Pauli, the plus state by the X, etc. Some interesting states, maybe the Bell state is stabilized by ZZ and XX, but also by minus YY. So if you multiply these 2 Pauli strings, you get minus YY, which also stabilizes this Bell state, it turns out. So really, this is the generator of some larger set, but we only have to store the generator. Now, what happens if you want to apply the Hadamard gate on this Bell state? Let's say we apply the Hadamard gate on the 2nd qubit, we only have to update the 2nd column. If you recall from the previous slides, Hadamard applied to Z gives us an X, and Hadamard applied to X gives us a Z. So we get this new stabilizer state represented in this tableau. Okay, now we move to decision diagrams where we also want to represent any quantum state. So this is for universal quantum computing. And how to think of these decision diagrams? Well, basically they represent pseudo-Boolean functions. This is a function from the bit strings to complex numbers, or to any semi-real. This makes it suitable to represent quantum states, right? Basically, it's a function from basis states to the amplitudes. And when we view a quantum state like this, we can immediately apply the Shannon decomposition that is known from the classical world. Basically, we take the quantum state phi and we peel off one qubit by setting it to false. And then we get some remainder state over n-1 qubits, which we again represent in this formalism. Or we set this qubit to 1 and we get some other remainder state over n-1 qubits. And then we do this recursively until we end up with the amplitudes. Leaves. Okay, let me illustrate this with an example. Say we want to represent this state. We can build a decision tree where each of the levels here represents 1 qubit. And this dotted arrow basically means setting the qubit to 0, and this one means setting the qubit to 1. So if we follow this path, this corresponds to the amplitude for the 0, 0, 0 basis state. Now we can get rid of the zeros in the leaves to make it more readable. And then we observe that often once we start filling in some of the qubits, we end up with nodes in the diagram that represent the same subvector. So both here represent 1, 0, both these two nodes, so we can merge them. And then we end up with a DAG. We no longer have a tree. And in practice, it turns out you get a very succinct DAG. It's for interesting states, it's no longer exponentially sized. So that's why these diagrams are so interesting. Also because we can apply operations on them to do computations. In the next step, so we call this an algebraic decision diagram or ADD, because the amplitudes are in the leaves, more or less. But we can also realize that we can divide out these amplitudes and put them on the edges. Then we get this structure, and then we can observe that these nodes all represent subvectors that are equivalent to some constant vector. And we can divide out on the level above, basically merge these nodes and put the weights edges. So this one represents.
Before that, so you somehow went, you said you could put the values on the leaves, you put them on the edges.
Yeah, so we end up with only one.
Why?
And then we divide out.
Why didn't you put the one on the edge too? What was special?
Oh, okay, you can think of this like there's the one on this edge.
Okay, and then the remaining, like now this one, we shouldn't think of it as a leaf, it's some sort of just like sink or something.
Let's just see.
It has nothing to do with like that edge specifically, that wasn't one. It has no special relationship with the one.
Well, we can choose to keep it 2, and then we would get different weights here. Basically, you multiply the weights with the and then we can do this for the level above as well, because we see that this one this node represents this vector, and this one represents 2, 0. So we merge these nodes, but we put the weights then on these edges, one level above. Then you get this structure. So maybe another way to think of it is like in this tree, we never merge nodes. Here we merge nodes when they represent equal subvectors. And here we merge them when they represent equal subvector or equivalent subvectors up to some constant complex number. And then we get something that is often called a QMDD, and it can be exponentially more succinct than the ADD. Now, why is this interesting? Well, we can succinctly represent many interesting states. So often the number of nodes in the DD, in the decision diagram, is smaller than exponential, based on empirical results. I think of it like a homomorphic compression scheme, like a homomorphic encryption scheme, right? You encrypt data and you do operations on it without decrypting. Here we compress data and we do operations on it without decompressing. How does this work? Well, say we want to apply a NOT gate to this to some quantum state. We basically have to flip the vector like this. In the decision diagram, we only have to flip the 2 edges. Oh, that's it. In general, we can apply any gate to a quantum state represented as a decision diagram. And not always, but often we know from theory that we get something out that is not much larger, only some factor larger. And the operation of applying the gate on the decision diagram is also polynomial time. Not always, but often. There are some details.
The hardest is like a swap, right? Like to find like the first or last qubit, because that completely reorders your tree.
Yes. Yeah. Lots of details. I think in ADD this would still be easier. Because in the sense that it only doubles the size.
But aren't you implicitly having for every vertex like a label which qubit is about?
Sorry?
Like, I mean, can't you just like in every vertex, it's there's a label saying like which qubit you're deciding.
Yeah, I
to
think
go right now.
that would be clearer. I have that later. Let me see. No.
Because then if we just swap those labels, then
Oh, like that. Yeah. So this only works if you have a fixed order on your variables, on your qubits. And if you want to combine two decision diagrams, you need the same order in both. So you cannot, if you start swapping in one, then you cannot combine. Okay. This is nice. This worked well in practice, we found, or other people found, actually, I should say. But we also found some limitations, namely that the QMDDs are not succinct for stabilizer states. And as I mentioned before, this is actually a problem if you want to represent quantum information. We have a theorem that shows that if you want to represent this grid graph state, which is basically a stabilizer state with the following tableau, then you get an exponential QMDD. Why is that? Because however you split the grid graph in two, you will always have n cross edges. And this is actually not so easy to prove, I found out, but I found it in some nice, in some old paper, which I found kind of interesting. They have a nice proof of it. And using this result, we can then show that in the middle layer of the QMDD, we will always get exponentially many nodes that cannot be merged, right? That are not equivalent up to some factor. So this is bad, and we wanted to do something about this. We basically wanted to combine the stabilizer formalism with decision diagrams, and Arjan has worked on this a lot, also other students of mine. We came up with the local invertible map decision diagram, and this is a generalization of QMDD. So we take the QMDD, but we no longer merge nodes up to a factor, but also up to a Pauli string. So we can use the Pauli strings to merge more nodes.
Or now are you having now edge labels that are like Pauli strings?
Exactly. So here's an example. We represent this state as a QMDD, and then we can see that we can use this Pauli string with Z tensor I to kind of work away this -2. And then the -2 becomes a 2. Therefore, these nodes can be merged. Yeah, so we kind of trade off the extra storage on the edges for merging more nodes in the diagram. And this pays off because, yeah, now we can represent all these grid graphs or graph states efficiently, and also stabilizer states efficiently. What we see is that for these graph states, we always get such a tower LIMDD, where the Pauli strings on the edges basically correspond to the adjacency matrix graph state. And we can prove that this always holds for stabilizer states in general. So any stabilizer state will always give us such a LIMDD that is a tower. There's one price we pay for it. Basically, to do operations like applying gates and measurements on LIMDD, we are cubic factor slower than QMDD. Why is this? Because the data structure has to be made canonical. We have to merge all the nodes if they can be merged. And now we have to do the Gaussian elimination on the stabilizer groups, actually, or at least on the generators. And this gives us this overhead. But in theory, it's still a nice addition. And we can then show that we can also in LIMDD be exponentially faster than QMD for simulation, and we're never slower. We're never more than polynomially slower.
So I say is never slower, you mean more than the polynomial factor?
Yes.
Okay, yeah.
I should- Um, why is that? Or no, one other thing is that we can kind of also do the simulation of Clifford circuits. Basically, if we have a stabilizer state, we have such a tower representation in LIMDD. And if we apply the Clifford gate, we again get a tower out of it. So we can show that this is all polynomial black. So this gives us what we initially wanted. And then we were interested in comparing this against stabilizer rank-based simulation. What is stabilizer rank-based simulation? It's basically the Tableau method that we discussed before by Gottesman and Agason, but now for universal quantum computing. So if we apply a T-gate, we again get this summation of Pauli strings. So with an example, we represent the Bell state here with the Tableau. We apply the T-gate, nothing happens for the Z, but for the X, we get a sum. Get a weighted sum of Pauli strings. So the Tableau kind of blows up for every T-gate. That's how you think. It's fixed parameter tractable in T-gates. And we found that for this stabilizer rank-based simulator, computing the W state takes exponential time because computing the W state requires a linear amount of T-gates, according to this work. And we can show that the circuit for computing this, any W state can be efficiently simulated using LIMDD. So LIMDD, there are some cases where LIMDD can be exponentially faster, stabilizer rank-based methods. We also implemented it, but I have to admit here, this cubic vector overhead really kills us. So we could at least find one example involving QFT where LIMDD becomes faster than QMDD. But yeah, I think a lot of work is needed to make this more practical, and we're currently looking into that with Agile. Okay, the last thing I want to talk about, maybe in 5 minutes, I'll just go over it quickly. So we wanted to compare these data structures against each other, and also asymptotically again. And we were inspired by this knowledge compilation map by Darwich and Marquis. It is seminal work, in my opinion, that really shows nice trade-offs in ways of representing standard Boolean functions. So we can represent a Boolean function as a circuit, but we can also push the knots down and we get a negative normal form. And from there, we can constrain further with other constraints, and we get a decision diagram, or we get CNF, or we get DNF. And all these normal forms have different properties in terms of succinctness and tractability of operations. So this diagram basically compares the succinctness, and we see that BDD is incomparable to DNF and to CNF, but DNF is always smaller, more succinct than BDD. So there can even be, this represents an exponential separation also in terms of succinctness. And then again, they compare also the trade-off with applying a conjunction on such a data structure. And they really create a nice map of comparing these trade-offs. We wanted to do the same for these data structures. So we looked at the different decision diagrams, the restricted Boltzmann machine and the MPS that I discussed before. And again, we want to compare succinctness and tractability of operations. What is an MPS? Well, the simplest definition that we could come up with is you take a qubit order, and then an MPS for representing an n-qubit state is basically two series of matrices. So the 0 matrices and the 1 matrices. And the interpretation of this MPS is basically the following. If we want to know the amplitude for some basis state, we basically multiply the corresponding matrices. So if let's say we want to know the 0, 0, 0 basis state amplitudes, we multiply all these matrices, meaning that their dimensions should somehow match everywhere, right? What are these dimensions? The largest dimension here is basically the bond dimension. And this data structure is interesting because if there is not a lot of entanglement structure in your quantum state, then this bond dimension will stay small. So you can have small MPS to represent the quantum states.
This looks like a matrix branching program.
Oh, I don't know about that. It's a tensor network also, right? So representing this state is basically you can do by these matrices. So if you want this amplitude, we multiply these three matrices together. We want this amplitude, we multiply the 1, 1, 1 matrices together, etc. Okay, so we compared this to QMDD and we found that MPS is at least as succinct as QMDD, and the proof is surprisingly easy. We just look at the QMDD. Now we label indeed according to the qubits. So we have qubit 3, qubit 2, and basically we can create an MPS for all the zero edges. Basically, the zero matrices of the MPS represent the adjacency matrices in this decision diagram. And you see that the dimensions exactly match. So here we go from 1 to 2, and here we go from, we have 1 times 2 matrix, and here we go from 2 to 1, and we have the 2 times 1 matrix. So this is exactly, these matrices are exactly the adjacency matrices for the zero edges. And then we can also create the matrices for the 1 edges. So this shows that QMDD cannot be more succinct than MPS. But we also can show that MPS can be exponentially more succinct. And there's this state where basically the weight of every computational basis state is the basis state as a natural number. And it has been shown that this state creates an exponentially sized QMDD, but it can be efficiently represented in MPS. Okay, I have many more results. We can go over them, but basically we are finding states that are large in the one data structure, but small in the other one, right? We reason asymptotically like that. We can also do this for RBM. And then we get the following structure or the following results, where this again represents the succinctness. And we show that there's an exponential separation between MPS and QMDD and ADD. And also LIMDD can be exponentially more succinct than QMDD. Now, if we add RBM, then we see that MPS, RBM, and LIMDD are incomparable, like I showed on one of the first slides. So basically, these are useful for representing different types of quantum information, let's say. Each have their own use. And finally, the tractability of the operations. I just want to zoom in on one result, namely that in QMDD we get more succinctness, and we inherit the tractability of, in LIMDD we get more succinctness, and we inherit the tractability of operations from QMDD. So everything that was tractable is more or less tractable in LIMDD, except for computing fidelity and inner products on LIMDD. And there we can show that it's conditionally NP hard. And we can also show this for RBM. How do we do this? We have a proof. Basically, we look at the Dicke states. The Dicke states are basically the states where the only non-zero amplitudes have a certain Hamming weight. So Dicke state 2, 3 is basically a sum of these basis states where there are 2 ones, each basis state.
I'm a little bit confused, sorry. So ETH stands for exponential time hypothesis or eigenstate thermalization hypothesis. In this case, both of them are possible, so I'm very confused.
Sorry, I'm running out of time, so I went a little bit fast. Exponential time.
Okay, very good.
Yeah.
It's because we were talking about matrix product states earlier, so it's possible that we were talking about thermalization.
No, it's only conditional.
Okay.
But we look at the Dicke state and the graph state. So we take any graph, and then we can show that the even subgraph problem Turing reduces to computing the fidelity between these two states. Meaning that if we can represent these two states efficiently in our data structure, then computing fidelity is also hard in the data structure. And we can show that indeed, for LIMDD and RVM, we can represent these states polynomial size. Therefore, we have this hardness proof. And this depends all on the even subgraphs problem being intractable unless the exponential time hypothesis fails. And it's a result by Jeremy and Meeks. Now I'm wiping a lot of details under the carpet because actually for fidelity, this is for inner product, but for fidelity, we reduce to some even odd subgraph problem, which is a little bit more general, but we also show that this more general problem is NP, or is hard unless the exponential time hypothesis fails. Okay, I will skip these results because I'm really running out of time. The takeaways, we can use sharp set solvers to do quantum circuit compilation. We can use LIMDDs to beat other decision diagrams in representing quantum information. And then we have this knowledge compilation map to know how these data structures compare. Yeah, and the rapidity results I did not discuss. And much of this work is due to my team, mentioned here, and information you can find in these papers. Thank you very much.